Hello and welcome to another tutorial. We're going to continue on discussion of the new operator, and we're trying to monitor the amount of memory that JVM has or JVM uses. And we saw that the runtime class provides some useful methods to examine the behavior or the amount of memory that is available, or get some information about the Java heap, the amount of memory that is available. And we saw that we can use the free memory method to get an estimate of how much memory is free. And then we saw that basically when we launch our Java application, the JVM requests from the operating system requests that it gets some amount of initial memory. And then basically out of that, then it uses some of that memory for a stack frame of methods. For example, obviously the entry point to your application is the main method, which requires some stack frame because it has some parameters, command line arguments, and then you can also create local variables or allocate objects, etc. So free memory, this returns an estimate of bytes of memory that is free. Total memory returns the estimate of the total bytes of memory that JVM requests from the operating system right when you launch your application, right? And then max memory is the maximum amount of memory that JVM is allowed to request from the operating system. And again, this is a flag that you, as the user, the person who launches JVM, can specify. So operating systems have their own limitations, right? But then usually the current PCs have quite some amount of RAM, like 16 gigabyte is the normal these days. Some more advanced computers, they use 32-bit, 64-bit, 128 byte. So 16 gigabyte of RAM is the normal these days. But usually people also have 32-bit, 32 gigabyte or 64 gigabyte, or even up to 1 terabyte. So workstations that do heavy computation, or the servers that run Java applications for some commercial application, they actually can have much larger Java heaps, right? So the max memory is usually something that we set, and we tell JVM, hey, you are only allowed during the lifetime of this application, when you run it, you are allowed to only request for this maximum amount of memory. So if our allocations, usually we consume memory when we allocate objects, right? Because objects have states. Usually local variables are primitive types, and they don't really consume that much memory because we usually don't have that many local variables, right? And we said that all these methods in runtime, they return a long or 64-bit integer, because with 32-bit integer we can only have up to 4 gigabyte. But in order to have or count the amount of bytes to more than 4 gigabyte, we have to have a 64-bit integer. So these methods, they return a long, right? And if you look at the documentation, so a max memory, it returns a long, and we say that it's a native method, and it returns the maximum amount of memory that the Java virtual machine that you launch your application with will attempt to use, right? And again, this is not a limitation that operating system puts on the JVM. It's a limitation that you, as the person who launches the application, can tell JVM to have this kind of upper bound of memory usage. If there is no inherent limit, then the value Java long max value will be returned, right? So now obviously all the configuration of the JVM have some flags associated with them that you can use at the command line flags, right? That you can use at the runtime when you try to launch your Java application to basically configure the JVM. Now for the inside the Eclipse, for example, if you go to your run configuration and the arguments, you have the program arguments, right? And this is what that string array args is in the main method, right? Everything that the strings that you put here with a space in between them, they're going to be passed to that string array. VM arguments are the JVM flags that you can pass at runtime when JVM launches the application, and you can change the default values of some stuff, like what is the maximum amount of memory that the JVM can use, or what is the initial amount of memory that JVM can request, etc. Now you see Eclipse also has some other flags that it automatically configures. XX show code details in exception messages. This is very useful in the recent version of the JVM, for example, for null pointer exceptions, etc. So what I did, I created just a quick project, and then I copied the new operator class that we had to this project because I want to configure with different JVMs or JDKs. And previously in the project we had some other classes that didn't have a compatible syntax, for example with Java 8. So I just wanted to avoid compilation errors. So this class is fully compatible with all versions of the JDK because we're just calling the runtime, which has always been available. We have the GC method, which has always been available, and then free memory, available memory, max memory, total memory, or the number of processors. So these have always been available in all versions of the JDK. So let me close this and open this again. So what we're doing is that we're getting the runtime and we're asking for available processors, and this returns the logical processors, not the physical ones. And then we print the max memory and print the total memory. We try to run a GC and then print a free memory and print total memory. All right. So let's see what happens. So if we run this, all right. So what I'm actually going to do, I'm going to put the console here side by side. I think this is a better view. Okay, so let's put the console here and then put these side by side, and then okay. All right, so this is our console. We have available processor 8 logical processor, which means I have 4 logical or physical cores. Print max memory, and by the way, at the moment I'm running with JDK 16. So let's see what happens. We see that the max memory, the default is 4 GB, and we saw that JVM by default assumes compressed OOPS or 32-bit address or the address space for references or the pointers that it uses. And we said that with 32-bit reference, you can only address up to like 3-4 GB of memory, right? So that's why it says, originally it says the default max memory is 4 GB because the default assumption of the JVM is 32-bit pointer addressing. And then we have the total memory. Total memory is the amount of memory that JVM requests from the operating system when you launch your application. So 260 megabyte we are requesting at the beginning, and then we run a GC, and then the free memory is 17, but then the total memory becomes 20. And we said that this is because the GC, what happens here is that if we explicitly ask for GC and then the JVM accepts that, it realizes that okay, let's do this. And then if JVM goes back and looks at the total memory that it requested at the beginning and how much memory has been consumed until this line of code in your application. If there was really not much memory, JVM decides, okay, let's return some part of that original memory that we requested to the operating system because it looks like the application is not consuming that much memory. Again, JVM does for every version of the JVM that there are improvements with this speculative memory management. To some extent, these are very good improvements because if your Java application doesn't really require that much memory, then it makes sense for the JVM to return the memory back to the operating system. Now we can print the memory before GC and then do a sysout after GC. All right, so let's run this again. So maybe let's also okay, so let's put this here, and I'm going to actually print the max memory as well. So max memory, total memory, and then free memory. So let's do this. I'm going to copy and paste this also here, and then we say that before GC. So let's run this. So before GC, we have JVM assumes a maximum of 4 GB, which means JVM assumes let's use 32-bit pointers and assume that the application doesn't require more than 4 GB because our address space is 32-bit. and then we get 260 megabyte of memory from the operating system, and then in the beginning 257 is free, which means we only consume 3 megabyte. Where is that 3 megabyte consumed? It's consumed on some of the internal stuff of the JVM. There are some, for example, JVM has to load all the JDK classes into the memory. And those classes, remember, loading the JDK classes into memory, it means it loads the actual class definition, the class files into memory. But some of those classes have static fields that have to be initialized when you load the basically the class into memory. But until somebody creates an actual object of that class, you don't consume extra memory, right? You just load the class into memory in a way that you only know the information or the basically meta information about that class. So 3 megabyte is spent on just loading the JDK classes into memory and holding the definition of the classes and holding some information about them, which is good. I mean, it's a very small footprint. But then what happens here is that we are asking the JVM to run GC. And I think in the most recent versions of the JDK, this has become deterministic, which means if you explicitly ask for it, JVM kind of accepts that and tries to always run this, right? So after the GC, the max memory is still 4, which means the assumption about 32-bit references hasn't changed, or basically the assumption that your application is not going to require a 64-bit address space is still valid. And then, but you see the total memory has reduced from 260 to 20 because JVM realized that, okay, up to this line of code, we only consume 3 megabyte of memory, and that was actually from loading the JDK classes into memory. So it looks like the application doesn't do anything with memory, is not allocating lots of objects. So let's return 240 megabyte to the operating system. And as you can see, we are still, the free is 17. So we are still using 3 megabyte. And again, that's because that 3 megabyte was consumed before even entering the main method, right? You launch the Java application, you launch the JVM. The very first thing that JVM does is that, so it looks like 3 megabyte is used to load the JDK classes into memory. So we load those class files. Each class file is usually a couple of bytes or kilobytes, right? Because JVM has to load the bytes into memory to know the information about the classes, so that if somebody creates objects of those classes, then basically JVM knows how to do it. So basically what happens here is, again, using a new operator, we allocate objects of a particular type or class. But then before even creating an object, the JVM has to load that class file into memory. The class file just tells the JVM what are the fields that this class has, what are the methods, right? So it consumes some memory. So this is extra memory. And the way JVM avoids allocating, or basically the way the JVM works is kind of lazy initialization, which is very good for memory consumption. But then which means that if somebody tries to create a new object of a new class, now JVM has to do some extra work at runtime when the application is running to first of all find that class and then try to load that memory and then try to create new objects of that class. So it has some performance hit. So lazy loading, lazy initialization, or lazy loading. So this is called basically lazy loading. And that lazy loading also allows dynamic loading, at runtime. And this is a more advanced topic, and we will look at this later on. So what I want you to understand is that there is a difference between loading the class file into memory, which means just JDK loads the class file itself, which just tells the JVM what is the information about this class, right? What are the fields that this class has, what are the modifiers of every field, and what are the methods that this class has, etc., right? So that's the meta information or the footprint of the class. But then when we use the new operator, JVM loads that footprint or the information about the class to actually allocate objects in the Java heap. So this 3 megabyte is consumed by the JDK classes, or basically after we launch our application, it looks like JVM loads a lot of classes into memory, and then it consumes 3 megabyte, which is still pretty good, pretty small footprint by today's standards, right? All right, so we see that 3 megabyte, but then this dynamically shrinking the total memory is a good performance improvement. Last time I mentioned that this was added from JDK 16, but I believe it was added in the previous versions, maybe JDK 11 or so. So something about that, and we can try that. So I am going to go here and basically right click properties. I'm going to select a different runtime, so JDK 8, right? So what happens here is that now, and I'm going to also clean my project so that I ask the Eclipse to recompile with the new configuration with the Java 8. And let's see what happens if we compile with Java 8 and then run this application with Java 8. All right, before GC, now it's very interesting that the address space is still assumed 32-bit, but then the maximum memory is 3 gigabyte, not 4. It's very interesting, right? So the max memory, it looks like the 32-bit address space in JDK 8 doesn't allow more than 3 gigabyte. But later, after I believe JDK 11 or something, the 32-bit address space, it allows a maximum of 4 gigabyte. So they did something to improve this address space. All right, so we start with 245. Remember, JDK 16 used the 260, so we're using 245, which makes sense, right? And then we have 242 free memory before running the GC. So we are still using that 3 megabyte. But then after that, after we ask the GC, looks like the JVM accepted our call to the GC, and then we still have the max memory 3. But then the total memory didn't change, which means in JDK 8, the JVM after the GC, it doesn't do any reduction of the memory. It doesn't return any memory back to the operating system. So the conclusion is in JDK 8, dynamic memory reduction or returning memory to operating system does not happen. So this is definitely something they added after JDK 8. So it wasn't implemented in JDK 8. And then the other difference is that JDK 8, the max memory, which is determined by 32-bit address space for references, right? Max memory is limited to 3 gigabyte, whereas we saw that in JDK 16, it was 4 gigabyte. So there is some improvement, and I believe that's because they have improved the header files. Each object has a header file which is has the information about the address space or the addresses. So they have improved the compressed OOPS concept or compressed addressing 32-bit or something. So it allows to address 4 gigabyte before switching to 64-bit addressing mode, right? Again, more Java applications, the ones that you use write daily, and the ones that have a short life. So you just run it, it does something maybe 5 minutes, 10 minutes, and then it terminates. Applications that don't usually run for days or something, they really don't require a large Java heap, or so the default 32-bit address reference address space is actually very good choice for almost I would say more than 90% of Java applications that you run, right? Java programs. All right, so 245 megabyte, we after the GC we have 243 megabyte. So you see originally we had consumed 3 megabyte. After the GC, now we're consuming 2 gigabyte. So it looks like the garbage collector was able to basically return or improve the free memory by 1 megabyte. So it looks like when the JDK loaded the JVM loaded the JDK classes from Java 8 into memory, 3 megabyte was used, and but part of that was some sort of allocated objects that were never referenced. And I think that's the reason that after the GC we get 2 megabyte of memory used instead of 3 megabyte. So there's some improvement, but we see that the total memory didn't change, 245. All right. Now let's switch to another JDK 9. So actually, if I use JDK 9, it's going to default my JDK 15 because I don't have an explicit JDK 9 installed. So I'm going to switch to JDK 11 because I have an explicit JDK 11 installed. So the way Eclipse works is that you can set your compiler level, and if it finds an exact match for a JDK that has been used, then it's going to default to that JDK. I know that we're trying to compare the performance of the JVM. Therefore, not only the compilation, the level of compilation is important. I want to make sure that I'm using the exact JVM that comes with that version. Because if I set the compilation to 10 or 9, it's going to default to my JDK 15, which means the classes are going to be compliant with Java 9 syntax, but the JVM is going to be JVM 15, right? From JDK 15. But this one 11 has the actual JDK 11 installed, so it's going to use the JVM from that. All right, and I'm going to clean the project to make sure that Eclipse recompiles this class. So if I clean up and run this again. All right, and by the way, we can actually check the version of the Java that is being used, JVM. So sysout basically JVM version is plus I believe runtime also has a version. Version is a static method, so we can directly call it on the runtime class, runtime.version, right? And if you look at the documentation of this version, it can tell you returns the version of the Java runtime environment. So inside at runtime, you can check which version is actually being used. So it says that I'm using 11, which was LTS, long-term support, and this is the standard Oracle JDK, right? Before GC, we have 4 GB instead of 3. So from JDK 11, so JDK 11, it defaults the max memory to 4 GB, right? So it looks like from JDK 11, definitely they improved the 32-bit address space. We start with 256 amount of memory, and then we have 254 megabyte free. So we only consume 2 megabyte. After the GC, suddenly the total memory has reduced from 256 to 8, which is a drastic reduction because the JVM realized that it ran the GC and realized that, okay, your application is literally not using any memory. So, and then the free memory is 1 gigabyte, which means 1 megabyte, which means at this line of code, the JVM realized that the original 2 megabyte consumption wasn't really necessary. So it's very interesting that what happens in JDK 11, right? So let's save this and let's switch to JDK 17, for example, and I'm going to clean the project, and then let's run this again. So I'm using the version 11 long-term support, version 17. Again, the max memory is still 4 gigabyte. We start with 260 megabyte, and then the free memory originally is 257. So we consume 3 megabyte of memory. And it makes sense that the most recent version of the JDK, we consume 3 megabyte instead of 2 megabyte because more classes were added. So there's some more stuff that has to be loaded from the JDK before JVM hits the main method, right? It gets into the main method. So as the JDK gets bigger and bigger, obviously the original consumption as memory becomes larger because there are more classes in the JDK that have to be loaded into memory. After the GC, the max memory is still 4 gigabyte because this is determined by the address space, 32-bit address space. And then the total memory is now gone from 260 to 20. And then we are still consuming 3 megabytes, so the free memory is 17. All right? So this is how this works. I mean, I think this is a very nice way of looking at some internals. And again, these numbers, the max memory is exact, right? It depends on but then the total memory consumed, the free memory, these are more like estimates. So if you need to do something very accurate in terms of memory, then don't really rely on these numbers. But these give you a good indicator of what's going on. Now, what I want to do next is to show you how you can actually configure the JVM. So JVM has 2 memory flags. One is -x ms, and then you specify some memory with m or g. M means megabyte, g means gigabyte, and some integer numbers, right? So ms means memory, s means a start. This is the total start memory. That's this line, total memory, right? And you can set it either in gigabyte or megabyte. And then there is a -mx. X obviously means max, right? Mx means max, memory max, and then you can set how much max memory you want to allow the JVM to consume or to request from the operating system. And by the way, these are JVM flags, so these are some command line flags that you pass to your Java application when you launch the application. In Eclipse, the way you do it, you go to your run configuration that Eclipse creates. So let me copy this. Let's start with the max. And I'm using JDK 17. All right. So I'm going to tell JVM to use 2 gigabyte max memory. This forces the JVM to never go above 2 gigabyte. And sometimes your application requires more than that, so JVM crashes with a out of memory error. But for now, I'm going to launch my application, and as you can see right now, the JVM tells me, hey, you requested a maximum memory of 2 gigabyte. We are still consuming 258 megabyte, and then we requested a total memory of 258 megabyte. That's and then I can control this initial memory also with the other flag ms. So let's copy this and then go back here. So the way you pass multiple VM arguments is with you can separate them with a space. So this configures the max memory that the JVM is allowed. This configures the start memory. S means start, right? MS means memory at start, which is the total memory that JVM initially requests from operating system. Usually you don't set it, but if you really know that your application right from the beginning has to consume a lot of memory, then it's good to configure the JVM from the very beginning. So if I run this, we will probably see that this total memory at the beginning is going to be 1 gigabyte. Yes, so we manually set the max memory to 2 gigabyte. The initial memory consumption, we set it with ms flag to 1G, right? And then originally the free memory is 1G. Obviously you see that in kilobyte there is some difference, 1048 620, 1050 620. So it's but then I guess we are still consuming 2 megabyte, right? But because we are doing integer division, when we convert from megabyte to gigabyte, the fractional part is not shown here. So this is like 1 point something, 1026 megabyte is 1 gigabyte plus 2 extra megabyte, but we're not showing it here. I guess we could show it in the total memory if we put a point here saying that do a but then this has to be typecasted. So for now, let's assume that everything is integer and works fine. So what happens now? You see that the memory is 2. So the Eclipse, basically the JVM definitely defaults to 32-bit addressing, because there is no point of using 64-bit addressing when the max memory is limited to 2, right? Now let's see what happens if we try to set the max memory, for example, to 5 gigabyte. That's definitely something that we can do. So the max memory is defaulted to 5. We're still and note that what happens between total memory as free memory. So let's see. So this is very interesting. Let me write it as comment here. So when max memory is limited to less than 4 gigabyte, obviously 32-bit addressing is in place, which means all the pointers, all the reference variables consume 4 bytes instead of 8 byte, right? So let's see what happens in the total memory and free memory when we do this. And then what we do next is to change to basically more than 4 gigabyte. If we explicitly request the JVM to have a max memory more than 4 gigabyte, that definitely tells the JVM, hey, if the user wants me to go beyond 4 gigabyte, if necessary, that means I cannot use 32-bit addressing from the beginning, because there is a chance, there is a reason that the user is asking me. So JVM definitely defaults to 64-bit addressing, or so all the reference types become 64-bit or 8 bytes, right? So what we expect to see is that the total memory is probably going to be the same, but the original free memory is going to be different, because the classes that the JDK loads from memory, they have some probably local variables or fields that are type of reference pointers. So each one now consumes twice memory than the previous one. So let's see what happens. I think this is a very interesting observation to have. All right, going back to our so let's set this to, for example, 2 GB. Let's run this. This definitely forces it to be addressing. The total memory is 258 in this case, and then the free memory is 256. So let's say consumed memory is 2 megabyte, and so we originally requested 258 megabyte from operating system, and then the free after loading all the JDK classes and hitting the main method, we have a free memory of 256 megabyte, which means we consume 2 megabyte. Now let's switch to, for example, something beyond 4 gigabyte of max memory. So let's say we set this to 5 gigabyte. What this means is that the JVM is going to launch more than likely with the 64-bit addressing. So we are requesting a little bit more memory originally, just because Eclipse realized that it's going to launch with the 64. Basically, JVM realized that its address space has become bigger, right? That's why originally it requests a little bit more memory from the operating system. Now, in order to, so let's write this down. Later in the next step, I'm going to force the JVM to always launch with the same amount of memory, right? We have this MS, so that limits the amount of memory, or fixates the amount of memory that JVM is going to initially request from the operating system. But then what we see here is that the consumed memory in this case is actually 5 megabyte. It's almost doubled, and it makes sense, right? Because we doubled the address space. So every variable that was a reference type in the JDK classes, and they were loaded into memory, and then they used to consume 4 byte, and now they're consuming 8 bytes because the JVM has switched to 64-bit addressing or pointer size or reference type, right? Now let's go to set the let's go and set the max, basically set the max to still to 5 gigabyte, but then we're going to force the total memory to be the same as basically what we had before. So what we want is to have 258 megabyte, and then we want to see how much free memory we have and how much we have consumed. So let's copy this. All right, so we're going to start with 258. So here I'm going to say -x memory start, and then 258 M, capital M or a small m. Let's see what happens. And as you can see, basically the JVM decided not to, remember this flag is kind of like basically, I guess JVM has the discretion to whether accept or not. So right now, as you can see, JVM started with 268 instead of 258, but we are still consuming 5 megabyte of memory. And what's interesting is that because after the GC was ran, JVM is 260, so it never went below the amount of memory that we asked it in the total memory flag, right? This is the memory start. And after the GC ran, it still stayed above that 258 megabyte, right? So what this means is that that flag -ms tells the JVM, hey, if we run GC, never go below that amount of memory, total memory. So let's see. Let's set this to maybe, I guess 400, something very large. So, and then So we have we request 400. The JVM starts with 408 megabytes. So it requests a little bit more than what we said from the operating system, and then we still consume 5 megabyte. So if you set your max memory to more than 4 gigabyte, the JVM is going to launch with 64-bit addressing, and therefore the memory consumption of your application is going to be larger if you have many variables of type references, right? Because references switch to 64-bit size instead of 32-bit size. I hope you really enjoyed this lecture. Please stay tuned, and I'll see you in the next one.